Our speaker this evening has quite a lot of credentials. He's got a PhD in electrical engineering and parallel computing. He holds several patents in computer architecture and distributed computing. He had former roles at Bell Labs and Intel, and his last company was acquired by Microsoft. Please welcome the founder and CEO of ScaleOut Software, Dr. Bill Bain.
Save that for after the talk. See, they'll agree. Can you hear me okay in the back?
Oh, yeah.
Okay, I want to introduce Chris Villinger. He's with me. He's our VP of Business Development, and he's Dutch. All right. So, if anybody knows what this title means, tell me. I did this title so it would fit in with the group, but it really doesn't mean very much. I'm going to talk to you about in-memory data grids, which is a technology our company's worked on for the last 11 years. And I'm going to tell you about some of the innovations that have occurred more recently, particularly through Redis. How many people have heard about Redis? Good. How many people are developers? And what about Java developers primarily? Or C# developers? Anybody? Python, I guess? Yeah, all right. Web developers. Okay. All right, well this is, there's some code samples in Java and some in C#. I do most of my development work in C. Our server side is implemented in C, so you guys know more about Java than I do, just so you know. So when you find errors, they're not mine. In any case, let's go to the next slide. This is what we're going to talk about tonight. I'm going to give you an overview of in-memory data grids and tell you why we created them and why they were released in January 2005 by our company. I'm going to tell you just a little bit about our company and our products, so when I refer to product names by accident, you'll know what I'm talking about. You can hear me back there, right? It doesn't sound very loud to me. I'll go with yes. Okay. All right. And then we'll talk about using in-memory data grids for computing. In particular, what people have done for the last decade is do the computing in the client and use in-memory data grids as a distributed cache. You know, it started with Memcache. And then there was a technology, a Java technology that Oracle acquired. Does anybody know the name of that in the space? TangoSolve. And they had a product that's called Coherence, now part of Oracle Suite. And Gemfire is another Java technology. And then Gigaspaces came along. Gigaspaces is an implementation of Java Spaces that was created by Bill Joy. And what did Bill Joy do? Anybody know? Bill Joy created Sun Microsystems. Right. So, okay. And then more recently, what Redis has shown us is you can move computation into the grid and do predefined data structures in the grid. And by doing so, you can really offload the network by doing computation very simply in a straightforward way directly in the grid and not pulling data out of the client to do that computation. So the executive summary of this talk is by moving computation into the grid, you not only get better scalability, you have a simpler way to write your client programs, you take full advantage of the scalability of the grid, and it's an evolution in the use of this technology. So we'll go through some examples of that. Now what we focused on over the last 4 to 5 years is data parallel computing, using in-memory data grids to do things like MapReduce. In particular, we implemented Hadoop MapReduce to run directly on the grid using the Apache Hadoop APIs. We also have our own implementation that doesn't use those APIs and is somewhat faster. But the point is, it's data parallel computing, which is a field I worked in for many years. When Eric said I was at Intel, I was at Intel Supercomputer Systems working on parallel supercomputing, which was very popular in the mid-'80s to the mid-'90s, and then became less popular. Now it's back in stage, and everybody is doing data parallel computing again. So what comes around goes around in parallel computing, and now we see that in-memory data grids provide a very nice object-oriented way to do data parallel computing. So what I want to do is relate what Redis is doing to data parallel computing and show you how there's some kind of a synthesis there. In particular, how you can build extensible methods that run in the grid, and they can be single instance methods or data parallel methods. So that's the topics for tonight. That's sort of the subject matter. I hope that's interesting to you. This is not a database seminar per se. Okay, go ahead, Eric. Okay, ScaleOut Software, real quick. We were founded in 2003, went to market 2005. We've developed this middleware software. Chris doesn't like me to say middleware, but it's a software layer that's not a platform, but simply a layer that provides APIs to applications. And you know, with open source, this is sort of disappearing. It's becoming highly commoditized. The use of in-memory data grids for scaling application performance. In particular, there's the Apache Ignite project. Have you heard about that, I presume? And Bain has the commercial version of the Ignite middleware layer. And also, there are other technologies like InfiniSpan from Red Hat. And so this middleware for in-memory data grids is becoming very well deployed. I think Gemfire went open source with their technology as well. We are not open source, but that's another discussion, not for tonight. We stay closed source and for business reasons, and we are driving instead to add value to the technology in the area of computing, in-memory computing, in particular for what's called operational intelligence, which is the use of these grids to do computation in milliseconds so that you can provide feedback to a live system. You can think of countless examples where the ability to do a computation that's very fine-grained to deliver results immediately will provide value. The case would be pacemakers that are providing telemetry into the cloud, or these watches you have now that are taking your blood pressure and heart rate, being able to then take that data, combine it with the knowledge of the person, the knowledge of the source, look at the stream of telemetry, and provide immediate feedback if there's a need to. We were talking with some people at SUNY and working in this area, and the experts say, we have the algorithms, we know what to look for in your heart rate and the other parameters for your heart from a pacemaker, and we can tell instantly whether or not you need to be alerted to a problem. The problem is nobody does that computation in milliseconds. It's usually done offline or in the data warehouse, and people then come back to you and give you a report. But the ability to just move this computation right into real time, providing immediate results, will benefit people by giving them immediate feedback. Another area would be context-aware recommendations for an e-commerce site. So if you go to Amazon and you should do this, and really just look at the recommendations you're getting mostly what are called static recommendations or paid-for recommendations. Sponsored links you see at the bottom. You also see people who bought this product also bought this. But you don't very often see recommendations where they're watching what you're doing in real time and giving you an improved recommendation to help you find the product you want. You get some of that with the filters that are on the left side, but then once you use a filter, you're back into the world of having to find the product yourself. So context-aware recommendations is another area. Internet of Things tracking thermostats and plumbing in large office buildings and heating systems, all of that. And there are countless other examples. Rental car fleets tracking cars, looking for drivers that are erratic or lost. Well, we could go on and on. But anyway, this technology is expected to become central to implementing all of these real-time, in-the-moment operational intelligence applications. And we have a video on our website. I showed it last year here. You might find it interesting as an example of operational intelligence using this technology. So let's go to the next slide. This is our product line, and I'm just going to check the time here, so I'll go about 45 minutes. And I'm not going to talk about products. This is not a vendor pitch. And I went to a great deal of trouble to sanitize these slides to make sure that every time I could, I got rid of any product names. But our basic product that we introduced in 2005 was a data storage product, in-memory data grid for distributed caching. And then we added computation starting in about 2008, and it's through several versions. We added MapReduce, and that's where our focus has been until we started moving into operational intelligence. Let's do the next slide. So let me just give you a brief overview of in-memory data grids, one slide overview, and then show you some of the use cases that we've run into over the last decade. And so we've now been in the market with this technology for 11 years. You've seen about 425 paying customers running on about 10,000 servers. So in-memory data grids are designed for application state, for business logic state. That's fast-changing data, which typically in the application is object-oriented. So that's the reason in-memory data grids are object-oriented and not relational, for example, in their view of data. And they're designed to match language APIs and semantics very closely. So what you see stored in in-memory data grids are collections, tight collections of objects, so that you can access them through very simple APIs, in particular the so-called CRUD APIs, create, read, update, delete. So they're like little non-hierarchical file systems of objects. And objects are then serialized for storage in the grid, and then retrieved, deserialized, and hydrated as simple objects, say in Java. And I'll show you some APIs in a few slides. They also can be accessed by their properties. So if they're Java objects, by their Java properties, and that way you can retrieve a collection of objects that match the query selection that you have. That's not a typical usage model. The typical usage model is a key value store for hosting objects that are retrieved with create, read, update, delete, so-called CRUD APIs. There is a Java specification, I think it's JS 104, for the basic credit APIs. But that was done many, many years ago, and these APIs have evolved a great deal since then. Now, one of the key things that we do as a vendor, when you say, well, what is your value add in the middleware, is to add these two things, transparent scalability and transparent high availability. So what that means is, as the workload increases, you have more and more objects, more and more namespaces. You can just add servers on the fly and be able to spread the objects out across the servers. And then it also means that if you don't need as many servers, it can automatically, you can pull servers out and collapse the data back to a smaller number of servers. It also means that for every stored object, there's a replica on at least one other server, so that you can withstand a server failure. In particular, either a server completely stops or the NIC fails and you can't tell whether the server's there or not. So that's important because we run in mission critical applications. All the applications that I described to you are mission critical. That means you have to have transparent high availability and scalability. And I'm sort of emphasizing that because I'm going to compare this to Spark. Because I think people, they see in-memory computing and they think, oh, it's Spark, and Spark can do this. And I'm sure there's some Spark people here that are thinking, I think I can do all of this in Spark. So I want to show you how, where this is useful, where Spark may not be, and vice versa, okay? So just want to cue you up for that discussion in a minute. Let's go to the next slide. Okay, oh, there it is, what do you know? So, all right, so this gets a little ahead of the discussion. This slide is normally shown later, but I wanted to just cover this in the beginning, because it occurred to me when I was preparing this talk that often we go all the way through it, and then I get the question at the end, well, how is it different from Spark? So I thought I'd sort of put that to bed right in the beginning. So, you know, Spark has what are called RDDs, Resilient Distributed Data Sets. And these are essentially collections of objects, right? And that are distributed across servers. So at that level, it's a very similar model. And there's an in-memory execution engine. The key differences are that the RDDs are opaque. They're not designed for CRUD operations. So they don't intend, there are ways you can sort of hack Spark. And I think people are starting now to talk about working around it. In fact, there's a conference coming up in May called the In-Memory Computing Conference in San Francisco. Is anybody aware of that? There will be a paper, I think, talking about, you know, how do you add in-memory data grid capabilities to Spark. So that's what's coming now. But the problem is you can't really use Spark to host data that has to be incremented or updated on an object-by-object basis, because it's really designed to do parallel transformations of an RDD to another RDD. So that's one difference. A second difference is that Spark is designed for the data warehouse, not for live systems. And the original architecture was designed to run analytics, not to run operational intelligence. So as a result, they use a technique called lineage to recover when a server fails. And lineage requires that you may have to go back and rerun a number of operations. The net effect is you cannot guarantee the latency. You cannot make sure the latency is fixed for recovering from a failure, because you may have to run a number of computations to recover. So that makes them less suitable for a highly available mission-critical environment where, for example, you're looking at telemetry from pacemakers, and you want to make sure you can give a response within a fixed number of milliseconds. So those are some of the differences. I think the key thing is that we're really intending operational intelligence to run in mission-critical systems. And in fact, go to the next slide. I'll show you some of the applications. It's not on the next slide, but it's coming very soon. We deploy in-memory data grids both on-premise and in the cloud, and I think you'll see, you know, of course, on Amazon Web Services, you can run their version of in-memory data grids. So there are many examples of this in the cloud. One of the nice features about this technology with the cloud is that it's elastic. Both the cloud is elastic in its availability of hardware, and the IMDG is elastic in its use of servers to handle larger workloads. So if you're holding shopping carts for a florist, and it's Mother's Day, you want to add more servers to handle the traffic, and then after Mother's Day, you want to reduce the number of servers. And you can avoid capital investment in a large server farm and do this very naturally by deploying an in-memory data grid in the cloud. One of the challenges of doing that is the fact that clouds have servers with unknown IP addresses, unlike on-premise. So the client applications, which may be multi-server as well, have to connect to the servers in the grid. And to do this efficiently, a given client has to go to a particular server where the data it wants has been sharded. And in order to handle that problem, we have implemented a technique, we call it a grid mapper, that uses metadata hosted in the cloud, and as that metadata changes, the grid mapper informs the clients of where the data in the grid is and which servers are hosting which data. But that's one of the challenges of running in the cloud. So this comes from our marketer group. I just thought I'd throw it up since this is an evening talk. These are some of the actual applications. This has been a little bit sanitized, but when we show potential customers some applications of in-memory data grids, this over the last decade is how our grid has been used. And I'm not going to read through any of this, but you can see a variety of applications. But I'll just cite a couple of cases. So we're used to host airline reservations for a major airline that you know well, but I can't say the name of it. So live day of flight reservations. And that's an example where operational intelligence would be very valuable to help reroute people. So another case would be for doing shopping. So some of the large television-based e-commerce sites use us to host shopping carts so that when customers are shopping, they can get at their shopping cart immediately. And also, I sort of skipped over the geographic replication that we provide, but it also means that if a whole city loses power, they can shift their customers to another city where they have a backup data center and do that just within a few milliseconds. And there are other cases as well where this technology is used. I'm trying to think of one. Yes, a very large news service based here in New York in the Times Square area uses us to host news stories and to cache them so they can serve them very quickly. So these are some of the uses of memory data grids. Now, when we started out, we felt this technology was mainly suitable for low latency data storage of fast changing data on the left there. And then over time, we realized it has a lot of value for doing data analytics, so-called real-time analytics. But typically, real-time analytics, as I mentioned, is done in the data warehouse, and it's not real-time sensitive. And often it's addressing very large data sets running overnight to do deep processing. Well, in-memory data grids are a very nice adjunct to the work of Spark and other technologies like Hadoop, the data center in the data warehouse, because they can be used to ETL live data into HDFS for use by Spark or other technologies. However, we found that operational intelligence is really where we think this technology is going to see its greatest value, and that's by combining computation with data storage and integrating it into the grid, and that's what the subject of tonight's talk is. So we'll focus on the use of integrated computation to provide operational intelligence. Okay, so I just want to recap the data model. It's unstructured collections of objects by type, and I said something in the previous slide I didn't mention, but we follow a sequential consistency model. And not all in-memory data grids follow that model. So if you guys go back and look at Leslie Lamport and other people that did work on this in the 70s, sequential consistency model is very important because it allows you to write transactional programs with message passing between threads and make them run reliably, even though you have an in-memory data grid where servers are coming and going. Sequential consistency requires guarantees about how you store data and update replicas. In particular, you need to use an algorithm that either atomically updates all the replicas or at least updates a quorum of replicas. And so we're not going to talk about that, but it turns out that under the floor, the data storage model and the guarantees you give the application, most applications don't think about it, but they're very important. If you use an eventual consistency model, then that does not give you the guarantee you need to make sure that when you update the grid and then you pass a message to another thread and say, read the data I put in, it may or may not be there, depending on what happens to the grid. And that makes it much more complicated to write application code. So these objects tend to be rather heavyweight, and they have extended semantics, which we really won't delve into, but it's important to understand that in-memory data grids have evolved to provide things like a distributed synchronization, distributed locking, pessimistic and optimistic, timeouts, eviction, and in particular, go to the next slide. Okay, so I'm going to talk about access to a backing store and access to a remote site in just a second. So first of all, this just gives you an example of the APIs. These are standard Java APIs that are used in our product. And you see it's create, read, update, delete. We don't need to take any time on that. So click here and get and remove. Go to the next slide. Our C# implementation, I think, is a little bit more elegant because you notice the overloading of the index notation so that you can store an object in the grid. And this is a namespace in the grid, and that's an object key. And it looks just like it's an in-memory collection. So that reduces the use of this external in-memory data grid to looking just like an in-memory collection. It makes it very simple to use the basic create, read, update, delete APIs. Go ahead. You also can use those APIs to access through the grid to a backing store. So for example, you can read through to a backing store if an object is not found, or write through on an update. In addition to other policies that could be specified. I won't read all of that, but the point is that people often ask, oh, is it a cache? Well, no, in-memory data grids aren't a cache, but they can be used as a cache. And the way they're used as a cache is like this, connecting them to a backing store, which could be a messaging system, by the way. It doesn't have to be a database. And by doing this, you have the ability to retrieve data from a much larger data set than you can host in memory. Go ahead. And the other thing that you can do, which is interesting, and I think we're the only vendor that does this, is you can connect grids together at multiple sites over the WAN and make them look like they're one virtual grid that happens to span multiple locations. And this was actually requested by that large news service so that they could access data that's over in Asia just as if it were local here. And the value you get from this is that data can migrate from site to site transparently with locking guarantees, and do that all transparently without using different APIs, just using the basic CRUD APIs. And there are policies you can employ to mitigate the WAN latency. The WAN latency is what is the real problem, right, when you do this. And so proxying the data and caching it locally and having a well-defined policy for when you refresh it is important for this usage model. Go ahead.
Is this replication?
What?
Is this real replication, or this is
No, this
just
is,
extend the...
This is remote access to grids that are not local. Within each grid, there is high availability, and then if an object is not found, you might find it in another highly available grid at another location. It's so that you can combine grids into one large virtual grid, as if it were just one local grid.
But there's a master for each object?
Yes, in our implementation, each object has a master and one or more replicas, and that object uniquely lives at one site. And if another site retrieves it, then it keeps a cached copy of that.
But
so
you
there's
need to
one
go,
master.
You need to go through the master, or you can go to...
Well, I think I should move on, because this is just to give you a little color, that you can do more with CRUD than just access a local grid. We can talk about it perhaps in quick Q&A. I'm not cutting you off. It's just this isn't really the subject of tonight's talk. I threw this in just to give you the flavor that you can use CRUD APIs to do a lot more than just access local data.
No, but you mentioned that you do it and others don't do that. That's why kind of this is interesting talk.
It is interesting. It's just not what I'm going to talk about tonight. It is interesting, and there are a lot of issues. So you'll think about, oh, there's a split break problem. What happens if the WAN line breaks and all that? So yes, there's a lot of good stuff to talk about here. But I'd like
so
to
you don't guarantee actually here
well, let's talk about it afterwards, okay? I do make guarantees here, but I just don't want to take my 45 minutes to talk about it.
Wait, one more question.
All right, so you'll see why, because there's a lot more to cover. Okay, so parallel queries, the other way people have used grids. What I'm doing is I'm working towards why we're going to do computation in the grid. So we saw CRUD, APIs, create, read, update, delete. Now we're going to see parallel query, so you can retrieve multiple objects. The problem with this parallel query, we find a lot of customers, the first thing they do, because they're database people, is, oh, let's go do query, because it looks like an in-memory database, when it's really a key value store with which you can do query. You immediately just sort of bottleneck the network, and I'm going to give you an example in the next slide of how you just immediately bottleneck the network by using query. Query is great, it's important. A lot of our customers use it, but the problem is it's distributed, right? So you're querying all of the servers, and even though you're doing index lookup on each server, you may actually incur order in overhead to do a query, right? So you will, because you're going to look at every server and then merge the results. Now, if you think of order in clients doing queries, that's order in squared overhead and network load, and that means network saturation is sure to follow. So just here's an example. I don't think we need to go into the detail, but yeah, you can see how it's just another API on a collection of objects. I didn't really go into this, but this represents the cache factory lets you create an in-memory representation of a collection of objects held in the grid, and then you can do a query on that. And we have two versions, one in Java, one in C#. What's interesting, go ahead to the next one. The C# one uses link query, and if you guys know about link, distributed link query. I found out just about, we did this, I don't know, 8 years ago with a contractor. And then I found out about 3 months ago, somebody said, you know how hard it is to do distributed link query? They don't document it, you have to figure it out. And so it's actually, very few people do that. I didn't realize it, but we actually had a contractor who knew how to do that. But actually integrating link into the grid is non-trivial. But it leads to a very simple API because you look like you're doing local link, and in fact, you can go ahead and retrieve objects transparently using link query and never have to do access APIs to the grid itself. Go to the next one. Okay, so here's the problem with query. This is a real problem we ran into with a real customer. And the problem is that if you overuse query, you just saturate the network. And the problem is you're doing computation outside of the grid. This is sort of the last stepping stone before you get to computation in the grid. Right? You're doing computation outside of the grid and pulling all the data out of the grid to do computation. So here, this is a real life customer who's that does perishable goods, and they track orders, a very large volume of orders. They're a very large, well-known site, and a very large number of inventory changes. And because they're perishable goods, they have a lot of inventory changes, and they have about 50,000 SKUs, stock keeping units, right? And so what they do is they create a namespace or a collection in the grid of orders and a collection of inventory. And then what they need to do is for each SKU, they need to pull out all of the orders and all the inventory and run a very secret algorithm to reconcile them. And then they can immediately say which orders can't be filled and alert, hopefully in real time, ideally in real time, alert the customer that no, we can't actually ship this perishable good to you because it won't be in stock at the right time when you want it. I won't go into any more detail on that. So the way they implemented this is they created a cluster, a compute cluster, which is just indicated here. A compute cluster sits out here, and here's a grid with another set of servers. And then they do essentially the equivalent of a parallel for each. They just deal out the SKUs to these, say, I think 12 or 14 servers, and have them start doing queries. For this SKU, query all the orders, query all the inventory. So the whole thing just stopped. It just didn't run. And of course, it's our fault, right? So we went down and talked to them, and we said, okay, there's 2 problems here. One problem is you're pulling all the data out of the grid to do the computing on it. And the other problem is that you have to join this data, logically join it outside of the grid. So the first suggestion is, why don't you pre-join the data by SKU, keep SKU objects in the grid, and then as orders and inventory come in, collect that information directly in the grid, and then next, run the reconciliation algorithm directly in the grid on the SKU objects. And they did that, and it just went blazingly fast. It went from 12 hours to 2 minutes. So it was a big win. Go to the next slide. So now let's talk about these techniques for moving computation into the grid. And this is a recap of not running it into the grid. So what happens when you don't run it in the grid is you have to pull data out of the grid and then run we just have this little depiction that you can see on most of forthcoming slides. That's a computation, right? And then you may push a state back into the grid, or at least retrieve state into the client. And so the problem with doing that is the network traffic that's going in and out of the grid. And Redis, made this observation that, for simple things like hash sets and for keeping scores, they have the Z sets in Redis, which keeps track for a set of users of their scores, and you can then rank them. So it keeps them ranked. Why are we pulling all of these scores out just to add one person's score, increment their score? Or, for a hash set, why don't we pull the whole hash set object out in order to add one new key value pair? So they said, well, why don't we move that into the grid? So go to the next slide. So the Redis, sorry. I didn't rehearse this enough, so I don't have the order right, but let me come back. So the problem with network motion is that it kills scalability. And I'll talk about the Redis approach in the next slide. So this is a slide we did for a slightly different purpose, but it conveys the same result. The way we look at how well the grid is doing, this is the key performance metric, is what's called scalable speed up. I think I talked about it last year, so if this is redundant, just wave and I'll stop. But this was originally, when I was at Intel, this guy named Cleve Moeller was hired to be our application guru. And he was one of the creators of LinPack. You know what LinPack is, linear equations package, with Jack Dongarra. And he was fresh from doing that work at Oak Ridge and came into Intel. and started trying to run it on Intel's parallel supercomputer at the time. And he got just absolutely dismal performance. It's just, he could not make the matrix multiplication go faster. And, you know, but being the brilliant person that he is, he's the creator of MATLAB. He said, I know what to do about this. And what you do about it is you don't run a given size matrix on going from 2 servers to 4 to 8 and hope that it goes faster. What you do instead is you run bigger matrices on larger collections of servers. So what you need to do is, as you add servers, you need to grow the problem size, and if you do so, the overall throughput hopefully will grow linearly, and then you will get parallel speed up. And then he wrote an ACM paper about this, and then another guy, John Gustafson, wrote a paper as well, and so Gustafson got credit for it, and it's called Gustafson's Law. So you can read about it. But Muller actually created it, or was slightly ahead of time. They both did it roughly the same time. But what you need is linear scalability in order to keep the latency of doing a given operation predictably low. So if we're doing this pacemaker, you know, measurements, and we're trying to report back to patients, and we're going to make a guarantee that we'll alert you within 100 milliseconds if we see an anomaly, then as we have 100,000 or 200,000 users, we have to add servers in the grid to handle them in order to make sure we have predictably low latency. If we don't do that, then the latency will go up, and some customers might take seconds or minutes. So what happens is, if you have a bottleneck, in particular network saturation, then you'll get this effect that the overall scalability will tail off. We measured this this is a financial services example, backtesting stock history, and this was done actually by a company called Lab49 that was on Wall Street last time I was here. You might have heard of them. And they showed us how important it is to avoid data motion. Go ahead. So now, the way you avoid data motion is you move the work into the grid. So I'm slightly mixing up data parallel and what Redis does, but they all weave together, and you'll see how they weave together in a few minutes, okay? So when you move the computation into the grid, then all you have to do is invoke the computation and pass the parameter to it. So you can see the amount of network overhead has gone down dramatically, and the work is being now done in the grid, and you're taking full advantage of the fact that in-memory data grids run on commodity servers and have multi-threaded, multi-core CPUs, and so they've got a lot of computing power. And instead of just using them as caches, using them as data parallel computers makes them much more useful, and it allows you to get this scalable speed up. And go to the next slide. So this is the way Redis implements a predefined set of operations. In particular, they have 4 different things, may have more now, but originally they implemented lists and hash sets, and what else? Sets of strings and sorted sets, as I mentioned, the scoring sets. So what they do is they build that code directly into their grid. I'll call it the grid service. This is the code that runs their in-memory data grid on each server. And so when you invoke a method, you're invoking it on one object in the grid. So that's mapped to a particular server, and that object, that's just called high tech here, because I couldn't get it changed in time. And then that object is just read, and the operation is performed in place, which means the data in here no longer has to be serialized, right? It can be deserialized data, and that's acted on directly by the grid service. So that makes it extremely fast, and it also makes it secure in the sense, or reliable might be a better word. It's reliable in the sense that it's pre-tested code that's been built by the people who write Redis. Now, we don't provide that with our product, but I think it would be a very good feature to add. And it is becoming increasingly popular. Go ahead. However, we have a different mechanism, which I'll talk about in a minute. So this shows you, as an example, Redis lists. And they provide these operators which can be invoked on a key, which means on an object in Redis, to do things like they have a list concept, and you can push on either end and pop from either end. And then you can do some really interesting things like trim the list from a range, a starting point to an end point. And then you can do blocking pops, so you could block until somebody puts something in the list. And you can also do a remove from this list and put in a different list. So here's a question for you, and I don't know the answer, so don't ask me afterwards. I thought of it when I was doing the talk today. I don't know. Hope nobody asks. But what if these 2 objects are on different servers? What does Redis do? My guess is they do it in the client transactionally, but I don't know. But does anybody know the answer?
There's a proxy.
Huh?
There's a proxy which knows how to spread
Yeah, okay, all right, we can talk more, but you know, okay, good, all right, please go on. Quick, okay. So some of the issues that you have here that I see with just using predefined methods running in a pre-canned, in-memory data grid are, first of all, in general, you have this problem that to maintain sequential consistency, Redis provides eventual consistency, but to maintain sequential consistency, you have to be able to execute methods to completion before you do the next operation on that connection. And that can slow down data access, in particular if the methods get complex or the objects get large. It also can become a hotspot. If one object, we found that we've had this problem consistently for 11 years, that customers will have a hotspot object, and we can spot it because all the servers are low CPU except for one. And if you end up with a hotspot object, then the value of the scalability of the grid is greatly diminished. But these are just, if you have to be critical, that's what you criticize. The main thing is that it's not an extensible mechanism. Now, Redis uses Lewis scripts for extensibility. And then you run into the problem of, if you run user-defined code in the grid service, what are you putting at risk? In particular, are you putting the grid service itself at risk? And their documentation says, yes, you do, so be very careful. In particular, they're worried that you'll use up the CPU in an endless loop and cause it to stall. Go ahead. So the alternative is you run out of process the methods that you want to run for the data structures hosted in the grid. So this shows you a set of service processes, which we call an invocation grid. These are worker processes that are part of this grid, which is a companion to the in-memory data grid storage processes. And so this is what we do in our product, but it's just a technique that one could employ. These would either be JVMs or .NET runtimes in our product, but they could be any kind of language runtime. And what happens is when a request comes in, it's sent to a particular host where that object code is hosted, and then that object is sent serialized to a worker, and then the function is processed, the result is sent back, and then forwarded back to the client. So some of the advantages of this approach are it's extensible. You can now run user-defined code, not just predefined code. Also, that user-defined code is separated from the grid service, so you don't compromise the security or the reliability of the grid service. Go to the next slide. And this is how that would run. So the invocation comes in, it's, as I said, the object is forwarded to the grid worker and the code is run. Now what's not shown in the slide is how does the code get there if it's user-defined code, right? So we'll talk about that in a minute. If it's predefined code, you just bake it into the grid worker. I think in real life, what you want to do is have some stuff baked into the grid service. The simple like the list could belong in the grid service, but some of the more advanced functions that you might want to implement that maybe or take more time, that you might want to pre-bake into the IG workers, and then user-defined code would always run in IG workers. Okay, go to the next. Can you go back one slide? Okay, so one of the disadvantages of this approach is the higher latency, because now you have to keep the objects serialized, no longer deserialized in the grid service, and then you have to migrate them up to the IG worker, and then you also have to have 2 hops to get the operation started, and then 2 more back to return the result. But that said, what you're getting as a trade-off is the extensibility by using an IG worker instead of the grid service. Okay, go ahead. So this is an example. This is sort of a concocted example. I wanted to just show you how the Redis lists could be implemented. So there's a lot of hand waving down at the bottom, just giving the flavor of it. The next slide shows you a real-life example with our product, how you do it. This just shows you in C# that yes, indeed, it's very easy in C# to write a list, a double linked list with your push and pop on both ends. And there's nothing magic there, except what you see here is the methods are defined here. Now, if you just call those methods from the client and pass the parameters to the class, the implementation of the class, boom, you've got Redis lists. And you could do this with an IG worker. And so this, at the bottom, if you can read it, just shows you how that might be done. And the idea here is that on the client, you invoke what we call single object invoke with the key that hosts this object here, an instance of this object, and you tell it which operation you want to do, and then you tell it the parameter that you want to pass. Now, what's important here is that how do you construct the delegate here that gets passed back? And that's where the code gets a little more complicated. In C#, there's one way to do it. We do it a different way. Go ahead in Java. So this is another example. Now, this also shows you, gee, we can use the same mechanism to do user-defined methods. And this is where it gets really interesting and valuable, right? So if you're an analyst on Wall Street and you want to do backtesting of stock prices, you can now do this in the grid with very low latency with a user-defined method. And that method here is defined right here now. And you can read this code as fast as I can talk about it, but you create a collection of stock price histories with PE ratios, and you have some analysis routine you want to run on them. So you instantiate this, right here in the grid, and then you actually, with this one, this is actual Java, running Java code with our product. You would just say for that collection, I want to invoke for, using this code here, and that key and that parameter, go invoke this method, eval, and then return a result. So with one line of code, you have implemented a user-defined method running in an IG worker. Go to the next slide. All right, so then how do you create the invocation grid to start with? And the answer to that is you have to solve two problems. One is how do you spawn the IG workers, and two, how do you pass them the code? And we spent a lot of time looking at how to do that. There are two very different techniques in Java and C#. In Java, what you do is you simply define this in-memory object which represents an invocation grid. You add all of the dependencies, the jars and the dependent jars, and then you set this invocation grid to the collection of objects right there, so that now you've associated the namespace of objects with an invocation grid. Go to the next slide. And then what happens is, the first thing that happens by doing that is that sends a signal to the grid and sends it the code. The code is stored in an object somewhere in the grid. So, this goes between code and data in a very unnatural way, but it works. The second step is we multicast to all the grid servers to start up IG workers. And the IG workers have a heartbeating protocol with their grid service for high availability. And the third step is we fire off a parallel operation to have them read the code. So they read the code and prepare to execute it. And that's all it takes to start an IG, an invocation grid. And the nice thing about it is you can have multiple IGs, right? Each namespace can have its own, and the user can control the lifetime, unlike the original MapReduce Hadoop implementation. The JVMs aren't taken up and brought down on every operation. You can start the IG workers and let them run for a month, and just use them over and over again for different operations. Go ahead. So now we're starting to tie this all together, and we're going to talk about the fact that you can get data parallel speed up with these single method invocations, because you get two advantages. One is you're handling multiple requests from a given client, so you can use this for stream processing. And I think one of our observations, this is one of the little secrets that we discovered about a year and a half ago that is really valuable, that instead of having a CDP engine that's handling stream requests or something like Apache Storm, and then keeping on the side an in-memory data grid as a cache, if you integrate these two with this technique of single method invocation, you can very easily do stream processing and have the advantage of being able to look at the state of the source of the data. So if it's a patient with a pacemaker, when the event comes in, you're not just looking at the sequence of events, you're looking at the patient's medical history, and what happened last hour, whether they just got an injection and they should, some medicine should have lowered their heart rate but didn't. You have all of this stateful information about the sources that you can combine with the events that are flowing in, so that you can provide feedback that's extremely introspective, that you can really look at this the streaming data and make better decisions on that data. So I do think that approach that I just described is not well understood, and certainly not well adopted, but I think there's a lot of value in looking at it, so pass that along to you for your consideration. And the other value you get is the fact that multiple clients at the same time can be doing these operations. So you have two forms of parallel speed up that emerge from using this approach. And just to show you, we have actually measured huge amounts of parallel speed up. This is another financial services application we did about 2 years ago. But it just shows you how you can look at, say, a terabyte of data and analyze it while it's changing. And do that in this example here in 4.1 seconds while it's changing at 250, you're analyzing it at the rate of 250 gigabytes a second. So it's like reading a whole terabyte disk and analyzing it in 4.1 seconds. while updates are occurring at 1.1 gigabytes per second, I won't belabor this other than to say that, you know, in real life, in-memory data grids provide substantial material valuable speed up for very large data sets that fit in memory. And the amount you can fit in memory, I get the question, you know, every time we get a talk, how much can you fit in memory? And, you know, every talk it changes, right? So, you know, it's not uncommon to have, say, 10 terabytes of memory available for a single grid today, and that's probably low for some applications. Go ahead. So the final step, the next step here, but the final step for our talk, is talking about actual data parallel methods and see how they're different from single methods. So data parallel methods are really sort of a form of MapReduce. You know, MapReduce, as Eric said, is two phases of a data parallel invocation. So we're talking about here as a simpler model. We implemented this for our product because I first saw this when I was at Intel. This is what the national labs implemented for MPI, message passing interface, for supercomputers at the time. And this is just simply an object-oriented implementation of the MPI multicast data parallel execution distributed merge. I was actually, when I learned how to do MapReduce the first time, I thought it was this and it wasn't. And then I thought, okay, well, where's the distributed merge? And there isn't one. And I was quite surprised that this wasn't the building block for MapReduce. But what we did, I had a Java engineer who actually observed that using this technique, you could very easily implement MapReduce as a map phase and then a reduce phase, using the grid for the shuffle step in between. In any case, what we're doing here is just running two methods now. One method to run this method on a collection of objects instead of on a single object, and then have a second method to merge the results. So now we're going to get true parallel speed up with one method invocation. Next slide. So now we do one method invocation instead of many, and we can run this method on many queried objects in the grid. I say queried because in our implementation, you don't want to necessarily have to pull all the objects out for evaluation. And then merge those results locally, and then merge them in, go ahead to the next slide, in a distributed fashion. This is an example that I showed last year. It's a financial services example for a hedge fund. We also demonstrated it yesterday at HBC on Wall Street. So what we're doing here is we're looking at portfolios, and they have long positions and short positions, and then there's a real-time live market feed. And what you want to be able to do is, as market prices changes, go look at all the portfolios in parallel and run code which is looking to see whether they're in balance or out of balance. If they're out of balance, to send an alert to a trader. So you can see this is, instead of operating on a single object, a given invocation operates on a queried set of objects. Go ahead to the next one. So this is the code that does that. This is the class definition, which has the long and short positions. In particular, it has this method here, eval positions. And that method is a method we run in the grid, right, to evaluate whether or not a trade needs to be made, an alert needs to be sent to a trader. Go to the next one. And so this code here is, this is the wrapper for that code to make it invocable in the grid. And then here is the actual code itself. Sorry, go to the next slide. The code that actually runs it is right here. This is Java example. So with one line of code, we can start a data parallel operation that does the parallel evaluation and the distributed merge and sends the result right back to the client. So you see it's very, very concise code, very simple, much simpler than MapReduce. No tunable steps, by the way. You don't have to worry about partitions and splits. And, but on the other hand, we're not moving traffic between nodes when one node finishes early, so you know, pluses and minuses. But the idea here was simplicity and very low latency. And it's relying on a good hashing of the objects across the servers to give you reasonably close finish times for every server. But the point is, with this very simple implementation, you now get real data parallel speed up. Next slide. And so what happens on every server, you're going to do this operation many times over a set of objects, not a single object, and then you're going to merge the results in each server and then across the servers. Go ahead. All right, so we're almost there now. This is almost the end. So how do you take advantage of both techniques? We learned about single method invocation and parallel method invocation. I'll use those terms, right? So you can either do an operation on one object, the Redis style on, say, on a list, or you do the parallel invocation on a set of objects. And also the single method invocation can be made extensible or not. So could they both be used in one application? Well, yeah, you know, this application of the looking at cable users, this is a real one. We have a customer that had this problem. They have something like 10 million set-top boxes, and this events flowing, channel change events flowing. And this is a streaming application, right? So it's a classic streaming application. And they need to be able to correlate that data, cleanse it for when people are falling asleep or just channels changing, and then be able to send an alert to a recommendation engine so they can upsell the customer. Or to somebody in their network support department if they see a problem with your cable system. And then also, they want to be able to look at aggregate statistics. So you see that the single method invocation is really good for handling the tracking of events. And as I talked about, we'll go to the next slide. Let's go to the next slide. This telemetry that's flowing in can be posted in with objects that represent cable boxes. And by doing so, just like the pacemaker patient, these set-top boxes know about that user, what their preferences are, what they've been watching in the last 2 hours, what they're likely to want to watch next. So it can do context-aware recommendations as well as correlate the data that's coming, the telemetry. This cable company said it took them 6 hours just to correlate the events because they dumped it all into a file system, read it out of the file system, and then correlated it all. But if you think about using the single method invocation, so in comes a channel change event, you immediately call an object, and you update a list in the object with the latest channel change event, and then you do the analysis right then and there, and maybe alert the recommendation engine right then and there. You can see the value of the single method invocation approach for a user-defined method for this application. Now, at the same time, you want to do data parallel analytics on all of the set-top boxes, say to find the top 10 most popular shows. So you might do a map reduce on all of the set-top boxes with a data parallel operation while you're doing these single operations to update the boxes themselves. And by the way, you're doing data parallel analytics on live data. So we're merging both of these techniques for the same application that's providing operational intelligence. And this is it, last slide. So you got through it. Not too bad, a little 5 minutes over. All right, so we saw that in-memory data grids, we first created them and other companies and open source projects did this for data caching. And I would say today that probably 90% or more of the uses of in-memory data grids are for data caching. But I came from the world of data parallel computing and parallel computing in general. That's what I've worked on since graduate school. And I saw many years ago the benefits of integrated computation into the grid. I never thought that in the lifetime of this company, though, that people would be adopting it. But with Hadoop, and then more recently with Spark, the desire to do computation in memory has just greatly accelerated. And however, I think there's an opportunity that grids offer that you won't get from other technologies, in particular this ability to do operational intelligence. That is to look at real-time state changes and reflect those as with object state in the grid so that you can enrich that state perhaps from offline data and then make very intelligent decisions that you forward back to the system and steer its behavior. And by doing this, you can enhance the business value of the system or the medical value for a healthcare system and use low latency in-memory computing to really drive not only value to the system, but a better user experience. Now, I just put that in at the end. A homework assignment for anybody who's interested is to now take so if we look at the Redis list, right, this is the last thing we're going to talk about. We looked at Redis list, and the list is encapsulated into a single object, right? I sort of punted on this thing, right? I didn't talk about this. And it was my goal for this talk to do it, but I just didn't get to it. I gave you examples of stock portfolios, things that are what Cleve Muller would call embarrassingly parallel. Do this operation on a whole bunch of these things. So like analyze all the set-top boxes, okay, but what if you really wanted to take a data structure like a list or a ZSET and make that a distributed data structure? So now you're going to have to shard the list or the ZSET into multiple objects, and when you do an operation, do you do a single method or a parallel method invocation to implement the Redis operations on it? And you would probably do a single method invocation, right? But then how do you do it in such a way you have multiple access with synchronization and locking, and you can get nice scalable throughput with heavy workloads on that data set? So that's something that I think would be interesting to look at. And And we've seen customers ask for that, by the way, and we don't provide it, but that's something you might find an interesting thought experiment after the talk. So that's it, and thank you very much for sticking with it. Thank you.
Thank you, Dr. Bill Bain. Let's start taking some questions. Yes?
Along those lines, if you're using these worker processes to do your computation, I imagine that you could have transactional issues and hotspots. So do you have tools for identifying them and managing them?
Well, definitely we have tools for hotspots. I'm not sure about the transactional issues that you're talking about, but let's talk about hotspots for a minute. And you always can get hotspots, and that's why it's important that you're dealing with large numbers in everything you do. So if you're dealing with Redis lists, you should have a large set of lists in the grid, and many lists that you're managing so that you can get nice scalable speed up by distributing the workload.
Right. I was thinking about that example that you mentioned, where this company was doing this rebalancing operation, and there was
reconciliation.
I think it was reconciliation. And so I can imagine that you write into a lot of these objects, and that would bring up these transactional issues.
Well, actually, there are no transactional issues here. I think the example we talked about a few minutes ago, where Redis is moving from one list to another, that's a transactional issue. But the issue I was talking about with reconciliation, it's simply a matter of, because the algorithm is designed to work with wide, fast-changing data, so you're going to read a SKU object, which has just been updated, but you're going to get a snapshot of it. You run the reconciliation on that snapshot, and that's the basis of the result.
Well, that brings up another issue then. So do you have the notion of multi-version consistency within the grid?
We don't implement multiple versions of objects, but some products do. So that's certainly something that people are interested in, but we don't do that in our grid because we haven't seen much request, or only one request actually, many years ago. Go ahead.
So on this subject, how would you prevent the dirty read?
Oh, that's a good question. Okay, so by dirty read, you mean read of stale data. Yeah, how do you avoid reading stale data in the grid? And that's where I said you need to have an algorithm such that when you are writing and updating in our case, we have a master copy and a set of replicas. They have to be updated either atomically or with a quorum algorithm, so that you're guaranteed after a failover and recovery event that you are guaranteed that the latest updates are in every copy of the new master perhaps, and any replicas that remain. We do that with a quorum algorithm, and I would invite you to, that's what we have a patent on that. Did that back in 2004. So if you look under my name, you'll see the patent on that. When I was at Microsoft, I worked on a product called Wolfpack, which is a clustering product, and they implemented quorum using a disk-based quorum, and then they had a multiple server quorum. But the idea that I patented was, why don't you have a logical quorum that you map to a sea of servers? So you can have different quorums mapping to the same set of servers, and that way, and that's how we implement partitions. Each partition has its own quorum replicas. And so when an update is done, when a write is done, it's done to a quorum, and then it's considered committed. So by doing that, you can guarantee after any failure that that update will persist because of the quorum. And because of that, you can then update the other replicas and make sure you never serve stale data. Now, there's another issue to stale data, which is the client cache. I didn't talk about it, but the client itself has a cache. And a lot of these products, some products, I'll just name one, App Fabric caching that Microsoft did, does not have a coherent client-side cache. Which means that if you just read, if you do an update to the grid and then you do a read, if it reads from the client cache, you'll get stale data. And you can't be sure. So that's why we make sure our sequential consistency model is pushed all the way to the client cache. And the way we do that is by version number checking. So when you do a read, we look at the version in the client cache and we go check it with the quorum. And if it matches a quorum, we don't return data. So there's a round trip cost. But the round trip cost, and you'll say, well, why don't you multicast? And there are lots of ways you can implement it. Hardware implements cache coherency with multicast signals because it's hardware buses. But when you do this in software, a pull model where you do a version check is a lot more efficient. And that's how we make sure all the way into the client cache, that you're guaranteed to always see the latest data, those two techniques.
That's all.
Go ahead.
That's all the time we have for questions, but Dr. Bain will be here for one-on-one questions. Feel free to come right up now. Thank you all for coming. Thank you, Dr. Bain.
Thank you.